Hello and welcome. Today we're going to talk about directional derivatives. Thus far, what we've done is we've looked at really derivatives of f of x comma y in the x and y directions. Okay, so just two directions, right? But the question is then, if we have this as our x and that's our y, we can either go in that direction or that direction. The question is, what if we want to go maybe in some other direction? How would we go about taking a derivative, figuring out the slope of the surface in a particular direction? How do we do that? Let's just get a picture to kind of get the understanding here. We have x and here we have y, we have z. Let's say we have a specific point x and y right there. And of course we have a surface like that. And we're up to a point right there on the surface. We've learned how to take derivatives in the x and y direction purely. But what if I want to take a derivative going in a very specific direction, like right there? Okay, and the idea here is that the surface might have undulations like that. I'm making some nice looking graphs there. Trying to make my best graphics here. So I want to know what the slope of the surface is in a really specific direction at a certain point like that. So the question is, how do we do that? Well, actually, what we're going to do is something very similar to what we would do, and recall just that any derivative is ultimately defined by some limit definition. All right. So first off, we're going to figure out what we mean by direction. So first, we're going to start at a very specific point. This is our starting point. Okay, that's our reference point. And then we have u, which is going to be our direction. So u is going to be a vector AB, and it's going to be a unit vector. All right, and that means that u in magnitude is equal to 1. All right, so that means the square root of a squared plus b squared is equal to 1. All right, with that, putting that together like so, what we want to figure out now is what do we mean by how do I do that? So again, of course, what we're going to do is if I blow this up right here for us, and if I think of that reference point, and that's my x0, y0 right there, okay? Now, if this is my u vector right here, and I'll put it in blue, okay, then that's going to be, if I think about a point right there, think of that as like some displacement, right? So what I want to do is I want to find the slope of this tangent line, or not a tangent line, I should really say slope of this secant line on the surface. Okay, but what we're going to do, of course, is move the points together. And when we move them together, what we're going to do is, and then form a difference quotient. Okay, to figure out how to do this then, we have a variable h as normal, right? We're going to take h to 0. But the idea here is we have f, and we're at point x. but then we're going to go displace a little bit by a, and multiply by h. And then we have y plus bh, right? And this corresponds to this point up there, right? And then, of course, we want to take the difference at x naught, y naught, like that, right? And then, of course, we'll do the normal thing, which is make that difference quotient. So clearly this is the rise, and that's the run right here. Okay? Okay, cool. All right, I think we have this. And the idea here, of course, is now we want to take h and make it go to 0. And we can call this something now. So I'm going to actually take this and make it a limit as h goes to 0. I'm going to actually call this something now. This is going to be called du of f, evaluated at x naught, y naught. Okay? So this is our notation for a directional derivative. And one really key thing about this is it must be the direction must be represented by a unit vector. Like that. That's the only thing. But this is going to be our notation, right? So you have f, and you have u, and you have the symbol d to represent derivative. Okay, cool. All right, so now what we want to do is actually take this limit. So what we're going to do here to take this limit is, again, we're going to expand, we're going to represent f by a linear approximation. And it's going to be this f here as a linear approximation from the point x naught, y naught. Okay, so we can clearly do this. F of x naught plus ah comma y naught plus bh is equal to f of x naught plus comma y naught plus the partial derivative of f with respect to x, evaluated x naught, y naught, times ah, plus the partial derivative of f with respect to y at x naught, y naught, times bh. Okay, cool. I think we have this. But now notice that if I take the difference there, so now what I'm going to do is I'm going to minus that from it. I'm going to minus here f of x naught, y naught. You see clearly that these will cancel. All right. So now if I look at my difference quotient again, and I'm going to move this down there. Well, actually, let's just select it and go to the next page. What we have here then is this whole thing here is going to be equal to partial derivative of f with respect to x at x naught, y naught, times ah plus partial derivative of f with respect to y at x naught, y naught, times bh, and we're going to divide by h. And then we're going to take the limit as h goes to 0. All right, well, I think from here, I think we can see that there's a clear, easy cancellation. The h's all cancel really nicely. And then we're ending up with the formula partial derivative of f with respect to x times a plus the partial derivative of f with respect to y times b. So this now is my formula. df in the direction of u is equal to the partial derivative of f with respect to x. Let's just do it. Let's clarify our notation a bit more. This is at a very specific point. Times a plus the partial derivative of f with respect to y times b. This is my formula for a directional derivative. Okay, great. I think we've covered some ground. And again, the key thing here is that a squared plus b squared has to equal 1. And what that means is, of course, is that the vector u has to be a unit vector. And that's very important. All right, so let's get an example going here of this particular formula being used. Let's say I have a function f of x comma y, and it's equal to x cubed minus 3y times x plus 4y squared. Okay, right, u is going to be the vector pointing in the angle pi over 6. Okay, from point 1, 2. Right, so that right there is my x naught and my y naught. Okay, so let's see if we can get a kind of a schematic here. There's my point there, and now I want to look at the direction going that way, pi over 6. Okay, that's the direction I want to look. So there's my u. Okay, so the question is, how do I actually define u if it's terms of an angle? And of course, I'm going to use cosine and sine. Right, and there's another way to write these. If you look up your unit circle, you're going to see that that's 1/2 there, and this is going to be root 3 over 2 there. Okay, so that's the direction we want to go. All right, now it's time to plug in and do the formula. So d of u of f, the directional derivative of f in the direction u, what we have to do is take the partial derivative of our function f with respect to x. So what we're going to do is, we might as well do that. We'll call it fx, and that's going to be, we'll do it up here in the top here. It's going to be 3x squared minus 3y. Okay, and the partial derivative with respect to y, that's going to be equal to minus 3x plus 8y. Okay, there we go. So now we have to put this in. We have a 3 times root 3 over 2. Oh, sorry, my bad. What is the point we want to look at? We want to look at the point 1, 2, right? So we put, we're going to have 3x, so that's going to be 3 times 1 minus 3 times, and y is going to be 2, right? So that's my fx, and then we're multiplying by root 3 over 2, plus, and now we'll take the derivative here and evaluate it at 1, 2, and it's going to be negative 3 times 1 plus 8 times 2, all multiplied by 1/2. All right, all we have to do now is just a small amount of arithmetic, and that's going to be equal to minus 3 times root 3 over 2, plus, let's let's look at this one. This is 16 minus 3. So, okay, that's going to be 13 divided by 2. Okay, so here's your final answer for the slope. That's how you use this to compute a directional derivative. Let's now try another one that we'll do on the next page. So now I want to try one. I'm going to use one of my favorite graphs, the hyperbolic paraboloid. And we're going to look at x squared minus y squared. Okay, so I can draw a graph of this one, which is good. I'm going to go from the point 1, 1, okay? And I'm going to look at u being, I'm here and I want to look at the point going in the negative diagonal direction there, so it's going to be negative root 2 over 2 and negative root 2 over 2, like that. Okay, let's just check to make sure that's correct. That should be pointing down in that direction. And u, in fact, is going to be equal to 2 over 4 plus 2 over 4, which is equal to 1. Okay, good. All right, so that's the direction we want to go. If I want to see the picture maybe drawn a little bit more in 3 dimensions, what I'm going to have here is this. That's an x, that's my y, and there's my z. And we know that it goes like that, and it goes down like that. And we are out here at 1, 1. And we're pointed in that direction. So if I'm going to look at a graph of this shape, it's going to kind of look like, that. And it should be climbing up. It should be climbing up some hill right there as it goes around of this saddle like this. Okay, so let's compute this. So, okay, of course, fx is going to be equal to 2x. Fy is going to be equal to negative 2y. Okay, all right. And now we all have to do is just plug in the values. So d of negative root 2 over 2, comma root 2 over 2 of f is going to equal 2 times 1 times root 2 over 2 plus minus 2, oh, sorry, this is minus there, times root 2 over 2 in the minus direction there. Forgot the minus there. All right, let's figure out what direction, what is the slope at this particular point. We have here going to be root 2. It's going to be a negative root 2 there, right? And then we're going to have here a positive root 2. So the slope is actually 0. That's pretty surprising. Let's see if we can get a better graph of maybe what this looks like. Let's figure out what's going on here. So we know that the parabolas go up and down, so there has to be a point right about in the middle where things must be stabilizing here. So if I'm right there, I'm actually going to be totally flat. I'll be pointed in a direction that's neither going up nor down. I'll be pointing right in a direction of towards the origin that is neither going up or down on the surface. It's totally flat. So that's really cool. There's actually a good way to understand this, and that's actually to examine the level curves. Of x squared minus y squared to understand what's going on here. So if I actually set it equal to 0, then I have x squared is equal to y squared, right? I want to figure out what points on the graph are flat, that stay even with 0. And we have this. Of course, then we're going to take square roots of both sides, but we have to remember it's plus or minus, right? right, and then we're going to get a plus x plus or minus x there, and that's equal to plus or minus y there. Okay, so we have to look at points, all the points that have this property. Well, clearly 0, 0 has that property, right? But what we want to know is, can we figure out what's going on here? So clearly, we have to look at all the combinations. So clearly, x is equal to y is one combination, and x is equal to negative y is the other combination, right? So that actually makes two lines. So if I actually were to draw those lines on there, one of them would be going this way, and the other one would be going the diagonal line like that, right? So clearly, the reason the slope of my surface is 0 at that point is because we're actually pointed on a level curve on that diagonal. Same direction as u is equal to negative root 2 over 2, comma, negative root 2 over 2 from 1, 1. Okay, so that, I think, gives us a clear understanding of what's going on here with this surface, and I think we've had some fun computing directional derivatives. All right, thank you very much.